Hi, I'm Mr. V, and this is Illustrative Mathematics, our text for this year. We're also using Unit 4, which is Right Triangle Trigonometry, and today's lesson is number 5, which is working with ratios in right triangles. So we'll start this. At the end of this lesson, you should be able to say, I can use a table of ratios of side lengths of right triangles to estimate unknown angle measures. And I can use a table of ratios of side lengths of right triangles to estimate unknown side lengths. That's what our objective is today. So we start with this picture and a rocket. When it climbs 50 feet, for every 13 feet it travels horizontally. Draw a diagram to represent the situation, and then estimate the rocket's launch angle. So if I start with the rocket here, and for every 13 feet it goes in the horizontal, it's going to go up 50 feet. And so this would be my angle that I'm looking for. What is the launch angle? And if we look at it from this angle, the 50 side would be the opposite side, and the 13 would be the adjacent side. So in my table, I have opposite and adjacent here. So I can write down the ratio of the opposite to the adjacent. Well, for some degrees, and I don't know how many degrees that is, I wish I knew, my ratio is going to be 50 divided by 13. And if I do this with a calculator, I do 50 divided by 13. Let's see, 50, move my picture, divided by 13. Oops, divided by 13. I get 3.8. 3.846, which would be round to 3.8. So this is about 3.8. Notice this is a ratio. It's a ratio of the opposite and the adjacent. And this is the number. This over here is also a ratio. It's written as a decimal, but it's still a ratio. And it's going to be between these two values. So it's going to be between 70 and 80. And I don't know the exact number. There's a way of calculating it, but we'll find that out later. But I know that it's going to be somewhere, maybe it's 75. I don't know, somewhere around in there. Our next activity. So we looked at some people's answers and we discussed it. Pythagorean triples. Pythagorean triples, in this activity, you will estimate angle measures in right triangles by calculating the ratio of the side lengths and using your right triangle table, which is the one that we just came from on page 4, to associate those ratios with angle measures. In previous activities we've done, we've estimated angle measures in a context. Here we're doing it with right triangles with whole number length sides. These are called Pythagorean triples. And you can look up Pythagorean triples on Wikipedia and it'll list for you. There's only 16 primitive or relative prime Pythagorean triples with a hypotenuse of less than 100. There's only 50 Pythagorean triples altogether with the multiples of the others that have a hypotenuse of less than 100. So that's something you can put your arm around and think about if you want to. So what does the Pythagorean theorem says? If we have a right triangle where A and B are the legs and C is the hypotenuse, then A squared plus B squared is C squared. What does the converse say? Well, the converse switches the arguments. It's if this, then that. It makes it if that, then this. So if A squared plus B squared is C squared, then we have a right triangle. So by the converse Pythagorean theorem, we know that a triangle with the side lengths of 7, 24, and 25 is a right triangle. Why? Because if A squared plus B squared is C squared, then it's a right triangle. So 7 squared plus 24 squared, that's 49 plus 256 is equal to 625. So the triangle whose sides are all whole numbers is called a Pythagorean triple. And that's what these are, 7, 24, and 25. Label the smallest angle A, 90 degrees for the angle C, and the third angle, angle B. And here we're going to find out, we're going to make estimates to find A and B. I'm going to go back a few pages to copy this, this table. This table will come in handy for us. It's not necessary to memorize it, but it is handy to keep on hand when we're doing our practice problems. So I will copy that to a new page. I'm also make it smaller here. I'm also going to copy the graphing paper for this problem. So this graph, I'll copy this down, and we'll actually draw this picture. And we'll make these ratios. So the if I were to draw this picture, I'm going to go 1, 2, 3, 4, 5, 6, 7. 7 is up, and I will go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So this distance will be my length of my right triangle. I'll draw it like this. And this would be the hypotenuse. This would be a 7, 24, 25. And I can label the sides. 7, 24, 25. The smallest angle we'll label A, this angle. This is C, the right angle. This other angle is B. Now, from angle A, from the perspective of angle A, we have the 7 is the opposite side. From B, 24 would be the opposite. But from A, 24 is the adjacent leg, and 25 is the hypotenuse. And going through and labeling this only takes a second. It really does make a difference in how you do things. I know several of these sides. I'm going to use 7 and 25. So my opposite to my hypotenuse ratio is 7 over 25, which is the same as 28 over 100, or 0.28. And what angle has a ratio of the opposite to the hypotenuse, which would be this ratio, of 0.28? Well, it's going to be somewhere between 10 and 20. So maybe 15, I don't know, somewhere around 15, because this number is going to be somewhere between this. Now, if you want to do more, you can do this with other Pythagorean triples. And like I said, you can Google Pythagorean triples. If I were to Google it, Pythagorean triples, and go down to Wikipedia, any of these would do it probably. But here you can list the 16 of the Pythagorean triples that are primitive, that is, not a multiple, like 6, 8, 10, or 9, 12, 15. So these are the primitive ones. There's only 16 of them with a hypotenuse of less than 100. And then they can list you several more, and there's an infinite number, but only a certain number have been found so far. All right. So going on to our deep dive, which is where we're going to solve all the triangles. First of all, what do you notice? What I notice is that there's one hypotenuse of a right triangle is 8.5. One of the other angles is 20. Angle C must be 70 because they have to add up to 180. I don't have either of the other two sides listed, but I think that I can find them given two parts of the right triangle. So I'm given the angle and the degrees. That's what I wonder. That's what we're going to be searching for. And there are several questions here. It might help you to set up a table. It may not. I don't know if it does or not. So here's our first question. And I'm going to take this question and copy it over to a new page so we see it. And I'll walk you through it. I'll also take this table and I'm going to copy it back over to the other page as well. So copy this to a new page. And now I'm going to look from 20 degrees. I'm given I'm supposed to find AB. From the 20-degree angle, this would be the adjacent leg. I'm going to write down here adjacent. And this is hypotenuse. Well, which ratio relates the adjacent leg to the hypotenuse? It's this one. And for 20 degrees, this ratio, this is a ratio. This looks like a decimal. Well, it is a decimal, but it's a ratio of the adjacent divided by the hypotenuse. And that's going to be in the x direction divided by the hypotenuse. This is going to be 0.940. And this is, if I divide this by 1, maybe you can see it easier. This is the same as x, we'll call this x, over 8.5. How would you solve for x? You can solve any proportion using the cross product property. So if I were to multiply 0.940 times 8.5, that would give me a value of x. I'll let you do that. Next, I'm going to go to cover this over one more time. We'll do the second problem. There's 4 problems in this set from Desmos. This one looks like it doesn't give us a picture. It only gives us a bunch of words. In a triangle with an angle measure of 40 degrees, the opposite of the 40 degrees is 5 centimeters. What is the measure of the hypotenuse? So if I were to write this down and draw a picture of it, I could draw a picture of this. I've got a right triangle. I'm going to draw a right angle. I don't know how much 40 degrees is, maybe this much. I don't know. This is 40 degrees. This is my right angle. The side opposite is 5. We want to know what the hypotenuse is. Notice this is the opposite. So which ratio is the opposite divided by the hypotenuse? It's this one. I'm looking at 40 degrees right here. So that's going to give me this ratio. So if I do the ratio, opposite to the hypotenuse is equal to 0.643. And that's going to equal to the opposite, 5, divided by the hypotenuse, which we'll call x. Now to solve this, I will cross multiply. I get 0.643x is equal to 5 times 1. So I divide both sides by 0.643. This is like a giant 1. So I get x is equal to this value. And you can calculate that. Let's see. In the Desmos, the next page, this is part of our deep dive. Here we have a picture, and it says we may want to redraw this. Why would we want to redraw this? Well, if it's not configured the way that we're used to seeing it, or if it seems out of place somewhat. So we could redraw this like this. I could go, I could rotate it. So there's the angle. This is the 50-degree angle. Next to these is 6. And I'm asked to find DE, so I'll call this x. Well, from this angle 50, it depends on which angle you're starting from, but from the angle 50, this would be the opposite, this would be the adjacent. So the ratio of the opposite to the adjacent is equal to, for a 50-degree angle, is equal to 1.192. And on the drawing, you can see that that's x over 6. This ratio is the same as this ratio. When I multiply both sides by 6, I get 6 times 1.192 is equal to x, and you can solve that. Our last one to look at, the fourth one, another word problem. So it's got some words in it that I have to interpret. I'll probably have to draw a picture of this. So I'll look down here. In a right triangle. So here's my right triangle. One of the angles measures is 70. Well, there's 70. This would have to be 20. The leg opposite the 70 degrees is 12. What is the leg adjacent to it? Did I do that last one right? I think so. What is the adjacent one? This would be x. This is the adjacent. This is the opposite. This is the hypotenuse. So if we're looking at the opposite over the adjacent of a 70-degree angle, it's this number, 2.747. That's going to equal to the ratio 12 divided by x. We can cross multiply here to find that x is equal to 12 divided by 2.747 when you're all said and done. You could calculate this in your calculator. Our synthesis. Strategies that you use to solve this. One strategy that I use that I'd like to see you notice you do, I mark the opposite from the reference angle, because if this were my reference angle, it would be different. I mark the opposite adjacent hypotenuse. That's something I would like you all to do. Lesson synthesis. You can talk about this. For the cool down, we have to find the angles on the sides of this triangle. And I'll do that. Again, I'm going to copy over from this page my table. And if the one angle is 90, the other is 70, the three angles have to add to 180, so this would have to be 20. From the 70-degree angle, this would be the hypotenuse, this would be the adjacent, and this would be the opposite. If I'm looking at a 70-degree angle, I'll be using these values. The adjacent divided by the hypotenuse, that is A divided by 7, which is the hypotenuse, is equal to 0.342. When I multiply both sides by 7, I get A is equal to 7 times 0.342. That'll be my answer for the length of A. For the opposite, if I use this ratio, the opposite divided by the hypotenuse is equal to the opposite divided by 7, which is, from here, 0.940. 0.940. And you multiply both sides of this equation, and you get O is equal to 7 times 0.940. This is not the number 0, this is the letter O. Let's see. Here's the lesson summary. And that's all I've got for you for today. Good luck and success.